Okay, in this video, we're going to see how we apply this strategy that we covered in the lectures to solve problems in mechanics. So just to run quickly through this, we have step one, which is identify all the forces that are acting in our system. And of course, we want to draw a diagram just so we can make sure we haven't missed anything. That's always step one. Step two is to use Newton's third law just to identify any equal and opposite reaction forces. So like the common ones that we will see are the kind of normal force of a surface acting on a body, or indeed the tension force. Third step is the kind of the moneymaker. This is where all the work is done. If we use Newton's second law then to determine either unknown forces or unknown accelerations, or indeed unknown masses, because that's what Newton's second law relates, the force to the mass and the acceleration. And of course, if necessary, we need to resolve those forces into mutually perpendicular or orthogonal directions. And oftentimes you'll see obviously horizontal and vertical directions, but frequently we will also see problems where we have particles on inclined planes, for instance, where those two directions, the ones that actually make sense, are the direction perpendicular and parallel to that inclined plane. So this is a kind of a necessary step when we have motion in two dimensions. In the example that we're about to see, we have motion in one dimension, so we don't need to worry about that step. We're going to see the other three steps in action. So here's the problem. It says a lift and its load have a combined mass of 1,600 kilograms. Find the tension in the lift cable when the lift, originally moving downward at 12 meters per second, is brought to rest with constant acceleration over a distance of 42 meters. So step one then is to identify all the forces and draw a diagram. So here's the lift and here's the load. And the force is acting on this, if we just think of this whole thing as a particle, well, we have the acceleration due to gravity, which is just the mass of this lift and its load times the acceleration. So if you think about it, this in and of itself is an application of Newton's second law, because this is the force acting given by the mass times the acceleration. Okay, oops. So that's the first force. The other force that's acting on this then is this lift cable is exerting a force upwards, and that's the tension in the lift cable. Now there is, of course, a reaction force, which is so this is the force of the lift cable on the lift. There is, of course, a force on the lift cable from the lift, okay? And that's why we usually draw tension as this kind of double arrow, because of course this is acting in both directions. There's a force acting on the lift and there's a force acting on the rope, and that is what we call tension. There is a reaction force to this force as well, but it's actually acting on the earth. So this is the force of gravity due to the lift pulling on the earth. So that's the reaction force there. So it's not really relevant for our problem that we're trying to solve. So these really are the relevant forces for the purposes of our problem. So that's then steps one and two. We've identified all the forces, drawn our diagram, and we've used Newton's third law, although all that's really given us is that there's this funny arrow that we use to depict the tension. So now we get to step three, which is using Newton's third law, which states that the net force acting on a body is equal to its mass times its acceleration. Excuse me. So let's write down what the net force is. And to do that, we need to sort of define our coordinate axes. So we're going to define this upward direction as the positive direction. So what that means is that the total force acting on this lift, well, we have the tension force acting in the positive direction, and we have this force due to gravity acting in the negative direction. That whole thing, this net force, is going to be equal to the mass times the acceleration. And remember that this tension is the unknown thing that we're trying to find, okay? Find the tension. That's what the question says. The twist here is that we actually don't know what the acceleration is. We're told in the question that the lift is initially moving downwards at 12 meters per second. It's brought to rest, and we're told over what distance that happens. And using that information, we can calculate the acceleration. We're going to use our kinematic equations to do that, i.e. the Suvat equations. So we know that the displacement is 42 meters. In fact, it's minus 42 because this is the positive direction. The lift is moving downwards. So we have a displacement of minus 42. Our initial velocity is minus 12 meters per second, because again, we're moving in the downward direction. The final velocity is 0, okay, because the thing is brought to rest. And the thing we're trying to find then is the acceleration. So we have these four quantities. The Suvat equation, the kinematic equation, which relates these, is this one, 2as is equal to v squared minus u squared. So let's work out what this acceleration is then. Let's rearrange the equation. First of all, the acceleration is going to be v squared minus u squared divided by twice the displacement. And if we just now substitute in the values that we've written down here, v squared is just 0, u squared is going to be 144, and twice this displacement, that is going to be minus 84, twice 42. And if I substitute in the numbers there, then I get an acceleration. These minus signs cancel out, so I get an acceleration in the upward direction of 1.71 meters per second squared. So I'll just note down that that's upward. And what that really means, of course, the lift is moving downwards. If it's accelerating upward, what that means is that it's slowing down. It's a deceleration. Okay, so this is our acceleration. And we're now in a position to substitute this acceleration into this formula to calculate the tension. So we have T minus mg is equal to the mass times our acceleration, which can now substitute in as 1.71. Just work with this a little bit. 1.71 plus g. Okay, I've just taken out a common factor of m there. And I can now substitute in my value for the mass, which is 1600 kilograms. 1.71 g, of course, is 9.8 meters per second squared. And when we multiply all of this out, we get that the tension in the cable is 1.8 times 10 to the 4 newtons. And that's our problem complete. That's the tension we were asked to find. So we've used our strategy. We, of course, don't need to use this fourth step because we've got motion in just one dimension, but we've used our strategy to answer the question.